Hello. Well, we're going to get in week 11, we're going to get to Dijkstra's shortest path algorithm. And this is what is often used in many shortest path processes like Google Maps and others to determine how to get from A to B at the shortest cost. So we're going to look at Dijkstra's in detail. We're going to mention Floyd's, but Floyd's doesn't return the edges that make up the paths. It just returns the minimum path length. So I don't find it very useful, but Dijkstra's is very useful. So here's method one. Method one is the one that Dijkstra originally came up with, and it's fairly complicated. It's what McAllister, the book, expands upon. And then method two is the way I learned, which is a little bit simpler. So we'll talk about both of those. They both result in the same shortest path tree. They're just a different way of couching it, really. So we end up with three data structures: the minimum path length, in this case from vertex 0, and the path edges that lead you there, and the shortest path tree, which is not in this graph complete. So Dijkstra's, as with many of these algorithms, is a greedy algorithm, which just means that at each step you look at the next best option rather than trying to maximize the whole process at once. So here's the algorithm in short. You place the starting vertex into the shortest path tree, in our case V0. Number two, you consider all the edges not currently in the tree from all the path vertices currently in the tree. And step three is the first place that it differs from Prim's, because Prim's algorithm takes the first two steps, but it looks at the next shortest edge. Well, we look at the total, in Dijkstra's, we look at the total minimum path back to the starting vertex, and we include the edge and the incident vertex. And then we repeat steps 2 and 3 until we are done. So here's a visual description. It's similar, but not exactly the same as Dijkstra's, as Prim's. Again, we have the same nomenclature, so green nodes and edges are in the shortest path map. And when we're looking at new edges, we have the red dotted line. So the first step is exactly like Prim's. We look at those shortest paths, shortest edges, look at those three edges that are incident from V2. And we find that edge 5 leads back to, gives the total shortest length back to V0. It's the same as the shortest edge. So we add edge 5 because 5 is less than 8 and 9. Same as Prim's. And then we look at the next, all the incident edges, again, just like Prim's. But now we add edge 2 just like Prim's, but for a different reason. We add edge 2 because 2 plus 5 is less than 8 and it's less than 9. So it's the shortest path, total path back to the vertex 0. So we add edge 2, and now we consider 3 and 8. 8 is more than 7 plus 3, so we have 7 to get to vertex 3. And then 5 plus 2, 5 plus 2 plus 3 is 7 plus 3 is 10. So 8 is less than 10, so we choose that edge and 1. And then, of course, the easy step, just like in Prim's, is the last edge. So this is the shortest path tree, the shortest path map. And so this graph explains how we would get back to vertex 0 in the least cost from any of the 4 other vertices. And here's the cost, the minimum path length. So still talking about method 1, we need to use several data structures. And here we initialize the vertices included. Remember, we had the values in there. And we take the adjacency matrix, the initial adjacency matrix, and we have this data structure that is going to hold the shortest path tree. That's what SPT stands for. And this is the edges that are in the tree. That's the 8 and 8 and so forth. And then the minimum path lengths. So here's the code. The pseudocode, sort of, except it's pretty close to Java. There are a couple of methods that are not defined, but find MinPath is one. So here's the code from that pseudocode for method 1. And there's the find MinPath code. Now you can use those in assignment 6, by the way, which is a graph, minimizing graph theory problem. So I looked over this algorithm and understanding that it was very hard to understand. I laid out these various data structures and how you would go from one to the other. So the first thing you do is take vertex 0, and this is a copy of the adjacency matrix. Vertex 0 already has the column for 0 zeroed out, so we're not considering how to get from 0 to 0. We're also not considering how to get directly from 0 to 1 because we have the upper right side of the adjacency matrix. So anyway, we look at these 4 and we find that 5 is the best way to get to vertex 0. And so let's go. So we look at those 3 along the 0 row, and we realize that 5 is the best, so that's vertex 4. So here we go to the adjacency matrix and zero out all the values, or put a maximum value so we never choose it again. We zero out the elements from vertex 4 because we will never choose again how to get to vertex 4. That is the best way. Now into the shortest path tree we put 5, and we also put the mirror image down here just because the shortest path tree is symmetrical. And then we put the weight that we took, which is 5, a total of 5 plus 0 actually. Put that in the minimum path lengths, and then we go back and put 4 as the second vertex that's included. Now at the next step, we want to look at 0 and 4 and the edges there, which are those edges, weight 8 and 9 and 2. Now we take 9 plus 0, compare it with 8 plus 0, compare it with 2 plus 5. And 2 plus 5 is less than 8 and 9. 7 is less than 8 and 9. And therefore we choose the next cost of the next edge of weight 2. And so that is vertex 3 to get to vertex 3. We zero that out just like we did before because we're never going to get to 3 any better way. And we put 2 in the shortest path tree because that's how we got to 3. And we add the weight that we used to get to vertex 3. And now we add 3 to the vertices that we included. In the next step, so I ran out of space on the slide, so I copied a new one. In the next one, we look at all 3 of the sets of edges, all 3 of the rows from vertices 0, 4, and 3. We don't see any cheaper way to get directly from vertex 0, but we still have the one edge 8. So now we go 8 plus 0, and 3 plus 7 is 10, and nothing down here plus 5. So vertex 4, vertex 1 is the one we get to via the edge that's weighted 8. So the minimum of 10, which is 3 plus 7, and 8, which is 8 plus 0, is 8. So that means that vertex 1 is the one we get to. Zero it out, we add them in, we add the minimum path length, which is 8, and we add vertex 1 to the graph, to the vertices we included. Now, of course, you can tell right now we only have one edge left, but we consider all the edges except 2, which is one we're trying to get to. And 1 plus 8 is 9. That's the minimum, the only cost. So we include edge 2, zero it out, include the weights, and 8 plus 1 is 9, so we include that. And then the very last step is to include edge 2 back in the vertices included, and we know we're done because the vertices included is full. So that's method 1. And so we've got this path edges matrix right here, and we could find the value, get from 0 by checking the path length from 0 to 2, for example. The edge in the previous, in this matrix, which we computed, is 9. So we visit each neighbor. 0 to 4 is 5, 4 to 3 is 2, 3 to 4 again is 2, 4 to 0 is 5. Eventually, we're over the 9 path length, so that's the path. This is one way of doing that. Okay, so that's method 1. Method 2 is the way I learned, and it uses set theory, the sets, an open set and a closed set. And the phrasing of the open and closed is just that closed means we have closed off the path to that node, and there's no other better way to get to that certain node than the way we've already found. The open set are those that are still open for consideration. Again, it's a greedy algorithm, and at each step you choose the vertex in open, and you set a backpath in the vertex that's enclosed in order to go back later and find the paths and move it from open to closed. So here's the same graph. Add V0 to closed, consider it's exactly the same graph, the same picture. Move V4, since 5 has minimum weight, move V4 from open to closed. And by the way, when you add V4 to closed, vertex 4, you set a backpath. Set the backpath, and it's just, in this case, vertex 0, so that you know how you got there. Same thing over here. When you find vertex 3, should be included in the closed set, you set a backpath from 3 to 4, because that's how you got there, and so forth. So it's exactly the same as the method 1, gives the same result, and it gives the same minimum path lengths. So here's the code, or the pseudocode, and basically for each vertex enclosed, adjacent, for each vertex in open adjacent to each vertex enclosed, you do these things. You get the weight, find the min path, and set the weight. And then you get the overall weight, and set, the last step is to set the back path of vertex 2 to the vertex 1 that it was adjacent to. So here's the code for method 2. Now you have this additional array called predecessor. I called it predecessor of, the predecessor of 2 is 1. In other words, 2 goes to 1. The predecessor of 1 is 0, so 1 goes to 0, and you've easily found the path from 2 to 0, the best path. You could do the same thing from 3. The 3 back path, the predecessor is 2. The predecessor of 4 is 0, so you follow that back. So let's just briefly talk about Floyd's, because I don't find it very useful, because you can't find the path, you can just find the costs. So basically, Floyd's is based on the idea that the commutative property, that if A goes to B and B goes to C, then A goes to C. And if the path length is less, then you replace the path length from A to C. So we won't go through that. But here's the pseudocode. It's fairly straightforward. 3 nested for loops and some if statements. And that gives you a quick overview of Floyd's, but we will be focusing on Dijkstra's.